So in today's video we're going to talk about facilitated diffusion, okay? So a cell contains K plus and a various monovalent anions. The membrane is freely permeable to both K plus and monovalent anions. An electric field that forms a membrane potential is maintained constant at -60 millivolts using a battery. It is stated that K plus is at equilibrium across the cell membrane and the temperature is 23 Celsius degrees. The concentration of K plus in a large volume of extracellular fluid is 10 millimoles. And here they ask us to calculate the intracellular concentration of K plus. And so first of all, we know they're talking about facilitated diffusion because we're having to do with ions, right? Remember, if it's small particles or molecules which do not have any charge, we're talking about simple diffusion. But now we're talking about facilitated diffusion because we actually have ions. And so the phospholipid bilayer cannot take these ions inside the cell or make them go outside the cell without transmembrane proteins, right? And these specific transmembrane proteins, when we're talking about facilitated diffusion, are called carrier proteins. And so these carrier proteins facilitate the movement of molecules or ions by binding to them on one side of the membrane, undergoing a conformational change, and then releasing them on the other side of the membrane. So this we call facilitated diffusion. So here they ask us to calculate the intracellular concentration of K plus, and we can utilize the Nernst equation to calculate the equilibrium potential for ions. So the voltage required to drive an ion down is concentration gradient. Okay? So the equilibrium potential, or the Nernst potential, is given right here for charged substance X, which is K plus in this context of potassium. And we simply need to put our values in and solve for Xi. So this is the concentration of K plus inside the cell. Okay? So the gas constant R is fixed to being this. The temperature we know is 23 Celsius degrees, which is the same as 296.15 Kelvin. Then we also know that the ion valence for potassium is +1. And the Faraday constant is fixed to being this. And then of course the equilibrium potential is actually given right here. An electric field that forms a membrane potential is maintained constant at -60 millivolts using a battery. So this is actually the equilibrium potential. Okay? So we simply insert our values and then we find that it comes out to being this. I forgot to mention that of course the concentration outside the cell is of K plus and the extracellular fluid is 10 millimoles. So this is XO here. Okay? So we insert our values and we'll find that the intracellular concentration of K plus is 150 millimoles. Okay? Now they ask, what is the concentration of anions inside the cell? And actually this is easy because this phenomenon is called electroneutrality, or the equilibrium of electric charge, which entails that the total positive charge from cations, so in this context we're talking about potassium ions, cations, must equal the total negative charge from anions to maintain a neutral charge within the cell. So this means that inside the cell we must have an equal amount of anions. So this means it must also be 150 millimoles, right? Now they say the membrane potential is now changed to -80 millivolts. What happens to the concentration of K plus inside and outside the cell? Calculate the intracellular K plus concentration when electrochemical equilibrium occurs at -80 millivolts. Okay? So we can utilize this equation. So the electrochemical potential difference between the inside and outside of the membrane for substance X, which of course has a specific valence. In our context, it's for potassium +1. Now, just to make sure you guys understand this here is the electrochemical potential energy difference, which is derived from taking the chemical potential energy difference, so the thing I'm marking right here, adding it with the electrical potential energy difference. So this is the chemical potential energy difference, and this is the electrical potential energy difference. Combining them gives us the electrochemical potential difference. Okay, so we know the gas constant, we know the temperature, we know the ion valence, we know the Faraday's constant. We also know that the concentration of the extracellular fluid, okay, which is given to be 10 millimoles. Now, of course, we also have the membrane potential, which is now charged to -80 millivolts. So this is given to being right here. Now, they're asking us the intercellular K+ concentration when electrochemical equilibrium occurs. So it actually means that, you know, at electrochemical equilibrium, the value is 0. So we can set all this to be 0 and solve for Xi, which is the concentration of K+ inside the cell. Of course, now it's changed to -80 millivolts, which gives us a value of 230 millimoles. Okay, so the intracellular K+ concentration when electrochemical equilibrium occurs is given to -80 millivolts. Excuse me, at -80 millivolts is given to 230 millimoles. So we can conclude that if membrane potential, because they're asking us what happens to the concentration of K+ inside and outside the cell, suppose you change it from -60 millivolts to -80 millivolts, well, what will happen? Well, we can conclude that if membrane potential gets more negative, right, so if the membrane potential gets more negative, then the concentration of K+ inside the cell will increase. So that is exactly what we've seen here. We've increased, or excuse me, the membrane potential is getting more negative, and we're seeing that the concentration of K+ is increasing. Okay, and so that's it. And then of course we have D here, what happens to the anions inside the cell. You guys should be able to do this very quickly because it's the exact same thing as B here, right? So the anions will equal the amount of K+, so 230 millimoles. I'm just going to write that quickly, 230 millimoles, due to the law of, you know, this law has a bunch of names, but for our context, let's just say of electrical neutrality, right? So the amount of positive charge is the exact same as the amount of negative charge.